Hello, I am Ahmad, and in this video, I'm going to talk about uh, mechanism of being plastic. This example, we apply a load in bar, round bar, which is diameter of let's say 30 millimeter, and then we increase the load between 2 points until one of the elements become plastic, and then we increase the load until the whole system is going to be plastic. And after that, we remove the load to see what would be the permanent deformation in the bar. So it is related to loading and unloading, and also residual stress that would remain inside the element after removing the load. Let's do so. Suppose we have one element with the length of 400 and 800 millimeters. At point A and point B, the element is fixed, and at point C, which is in the distance of 400 millimeter from A and 800 millimeter from point B, we have the force P. Some basic information for the calculation. Assume that diameter of the bar is going to be 30 millimeter, and it's with the material of, let's say, brass, with the modulus of elasticity of 100 gigapascal, and the yielding stress of 180 megapascal. Also, we can assume that the material is elastic, perfectly plastic. So it means that we ignore the hardening strain in this material. So now the question is that how much load we can apply to this point C intersection between two bars if they are with the same material, with the same cross section, but with different length. So when we increase the load, in the beginning, the system will be in elastic phase. If we sketch the relation between the strain and stress, the linear or elastic part will be up to sigma y, which is 180 megapascal, and the relevant strain will be epsilon y. We can calculate epsilon y by the equation of sigma y divided by E, so it will be 0.0018. So this value will be 0.0018, and after that it becomes plastic, and the material cannot take more than the relevant or plastic load. So before we start to solve the entire example, it is wise if we calculate what is the yielding force for each element. So Fy will be sigma y times A. So 180 megapascal times pi 30 millimeter power by 2 divided by 4. So it will be 127 kilonewton. So it means that AC or CB can resist 127 kilonewton. In this example, we ignore the buckling effect, which in this case, for example, element AC will be under compression. The length is quite small, so buckling might not be the dominant criteria here. So if the load is less than the yielding force in each element, then it means that the system is in elastic phase. In other words, AC and CB will be in elastic phase, and the equation of elastic deformation can be applied. Compatibility equation for point C shows that delta C in the AC side should be as same as delta C in the BC side. So the element is not going to rupture. And if we sketch the support reaction for this system, we have AX at point A, we have BX at point B, and we have the load P at point C. AC element will be under the force of minus AX. And BC will be under the load of BX. And from the equilibrium equation in X direction, you can see that AX plus BX will be as same as P. So the compatibility equation, which is delta at point C, is the absolute value. So it means that AC is shortening and CB is elongated. So as a result, we can write down delta from the elastic equation FL over AE. Now if we substitute the elastic elongation equation to this delta C should be the same for AC and BC. It means that AX times L of AC, which is 400 millimeter, divided by A times E for AC part. It should be as same as BX times 800 millimeter for the BC length, divided by A BC times. As far as we have the same rod for the entire system, so area is constant, and also we have the same material, then they can be crossed. And from here we can summarize that in elastic phase, AX will be 2 times BX. That is the main equation to solve this problem. Now we are going to increase force. In that case, we need to check which element will reach to its yield force first. In this case, as far as AX is greater than BX, so most likely or certainly it will be the first element, or AC is the first element to reach its maximum yielding load. Fy we calculated and it was 127 kilonewton. So I go in the other way. Assume that we think, or in other examples, that the materials are not the same. If we assume Bx is going to yield, one option is Bx is going to yield first. So in this case, Bx will be 127 kilonewton. And from equation 1, Ax will be 2 times 127 kilonewton, which is 254 kilonewton. And this is beyond the yielding force. It is greater than Fy of the element, which is 127 kilonewton. So this is not happening. As a result, our assumption or initial assumption is not correct. Then we have to come back and assume that, okay, Ax will be 120. And if we apply this value to equation 1, then Bx will be 127 kilonewton divided by 2 or 63.5 kilonewton, which is smaller than Fy 127 kilonewton. So this is the first step. We increase the load from 0 until a value that Ax or the AC internal force reaches to 127. At this point, element AC is on the edge of being plastic, and element BC is halfway, so because it is 63.5. Then we have the equation star. So from that equation or a star equation, we can see that P will be AX plus BX, which is 127 plus 63.5 will be 190.5 kilonewton. So 190.5 kilonewton is the value that P can be increased until one of the elements become plastic. So let's sketch what has happened here for the system, element AC and element BC. Element AC, this is formation, and this is the force. So the force in element AC is increased from 0 to 127. kilonewton. This is the load. And the corresponding deformation can be calculated according to FL over AE. So the force is 127 kilonewton times the length is 400 millimeter divided by area, which is pi 30 millimeter power by 2 divided by 4, and then 100 gigapascal. So this value will be 0.72 millimeter. We can calculate this directly from the strain. We have the strain Y times L of AC. It's the same. So epsilon Y we calculated and it was 0.0018. So it will be 0.0018 times 400 millimeter. Exactly the same, 0.72 millimeter. The corresponding value for the deformation in this point is 0.72 millimeter. And from here, the load cannot be increased. Let's sketch the stress and strain graph. So here, epsilon and sigma. So if the element is not supported by any other rods, so it starts and it's perfectly plastic, starts to yield, and then it will deform. But as far as steel, we have the element BC, which is under the plastic phase. It's in elastic yet, so it cannot, it is taking the rest of the load if the load is increased. As a result, from this moment, the load in the element AB cannot be increased. So it will be a constant value after reaching to this level of the load. So this is for element AC. Now we can check also element BC. For element BC, again, we can sketch the force and deformation and also stress and strain. Strain and strain, as far as it's the same material, so it's with the same graph, 180 megapascal correspond to 0.0018 strain. This is the graph, but the force in this phase, when P is going to be 190.5 kilonewton, the force in BC is 63.5 kilonewton. So the force and deformation graph can be sketched by the given value. So sigma or epsilon. So delta will be FL over AE. Still we are in the elastic phase, 63.5 kilonewton times 800 millimeter divided by pi 30 millimeter power by 2 divided by 4 times 100 gigapascal, 0.72 millimeter. So this should be exactly the same because we applied this compatibility equation to the system. So it should be exactly the same value. But the strain should be different because the strain is the deformation divided by original length. So first, let's sketch the force. The force is 63.5 over here. And the deformation in this stage is 0.72 millimeter. But still, the element has the capacity to take more load because if we calculate the stress, it's force divided by 8. So 63.5 kilonewton divided by area will be 89.8, almost half. 89.8 or let's say 90 megapascal. You can see that in the stress strain graph, we are in the 90 megapascal and it should be exactly half of this strain. Let's check it out. So strain in BC will be delta divided by LBC. Delta is 0.72 millimeter and the length is 800 millimeter. So 0.72 divided by 800 will be 0.0009, which is exactly half of the yielding strain. So in the force and deformation domain, it's the same. It can take up to 127 kilonewton and the deformation can come up to, you can calculate what is the delta y. Delta y is epsilon y times L, which is 0.0018 times 800 millimeter, will be 1.44 millimeter. So this value is 1.44 millimeter. Now, this is the relation between force and deformation domain and stress and strain domain for element B. Here we can see that in the elastic side, we still have capacity for this element. Before we increase the load to see what would happen, let's sketch also the force and deformation. This is the entire force of the whole system. So here, this is the force, this is delta, and this is for A, for force P. Better to write down that way. For force deformation is 0.72 millimeter with the value of the load, which is 190 kilonewton. These are not scaled, so and this is deformation at point C. Now we are going to increase the load to see what would happen. Next. I sketch the element one more time. This is point C, A, and B. So I increase the load force from 0 to 190.5, and then AC becomes elastic. It is better to write down that it is in compression. And BC is still in elastic phase. As far as BC is still elastic, so the system is not mechanism, so it can take more load. How much load it can take? If we come back to BC element, we can see that still we have 63.5 kilonewton capacity left for the element BC. A very straightforward approach to deal with that for this type of questions. Point A, point B, point C, and this is force P. The easiest method is to calculate Fy of AC and calculate Fy of BC. Then P, Y, or yielding force of P, will be the summation of these two forces, Fy of AC plus Fy of BC. At the moment, Fy is already 127 kilonewton, and this is 63.5 kilonewton, and the left capacity is 127 minus 63.5. 63.5 kilonewton capacity left. So there are different methods. We can say that at the moment it is 191.5, and we can increase by 63.5. Or we can directly calculate by summation of the yielding force of each element, which is 127 plus 127. In either case, you will get the same result. So first approach, 190.5 plus the remaining capacity of the element which is not plastic yet. So 127 minus 63.5 kilonewton. So it will be 254 kilonewton. Second approach, Py will be Fy AC plus Fy BC, which is 127 kilonewton plus 127 kilonewton will be 254 kilonewton. So now the question is, how we can sketch and what would be the deformation at point C at this level. Let's sketch the stress strain relation. So the first one represents the AC. The second one is BC, and the third one is F or P. So in the first one, I will go with the negative side. So this means that it is in compression. And the other side is for the tension. And we can go with deformation for now. So when the load is going to be 127 kilonewton, the yielding deformation for element AC will be 0.72 millimeter. So from now, if we increase the load, it is completely free to deform. It means that it cannot take any more load. So instead, whatever happens in terms of increment of the load, it will just deform. It's a deformable element. It's a plastic element. Let's sketch the same for the other element, which is BC. So at the load of 63.5 kilonewton, it was exactly 0.72 millimeter. So this is the time that the load reaches to 190.5. And it was 0.72 millimeter. It's better to sketch a line to show where we are. Different color. So this is point 1, point 1, and point 1. Point 1 represents when P equals to 190.5 kilonewton. Now we can increase the load for 63.5 until it becomes the yielding force of the system. So it means that we have only capacity to increase the load in the BC element here. And if we recall, the yielding deformation of BC element was 1.44 millimeter. So it can increase up to 1.44 when the load in that element becomes to be 127 kilonewton, which is the yielding load of the element. Meanwhile, in AC, the load cannot be increased and it is completely deformable. So it is just coming to the horizontal line up to the same value of 1.44 millimeter. So this is the phase number 2, or let's sketch it, name it number 2. So number 2 is when P is Py, which is 254 kilonewton. In the force displacement graph relevant to the force P, so we increase the load of 63.5 kilonewton. So the load will be 254. So if this is 95, so it will be somewhere here, which is 254, and the deformation will be 1.44 millimeter. So if the load comes to this level, 254, we can see that element AC was completely plastic, so it was deformable. It could not take any more load. In elements BC also, at this point, there is no resistance in terms of the force. So from here, the load cannot be increased. And if we apply bigger load, let's say 1 kilonewton more than that, then it starts to deform. So it is not statically stable. So what would happen from now? The system will be completely free to deform, and then it is called mechanism of the system. There is no uh, resistance for the system. So this is the concept of how to calculate the yielding force of a system, two rods. It can be different materials, different cross sections, or different configuration of the loads. So the next phase is to remove the load at one stage. So first of all, we need to understand that 254 is the maximum load that we can apply to this system. So the load that we can apply should be something between 0 to 254. Now we have two different approaches. First, the load is less than 190.5, or it's less than one of the elements becomes plastic. And the next phase is that if one of the elements is yield and the other one is still below the yield limit. So something between 190 and 254. So first example of the load. E is going to be 160 kilonewton. If the load is removed, what is the stress and strain in the elements? The answer is obvious. We will just cross-check how it works in practice. So second example of the load. So P is 220 kilonewton. If the load is removed, what is the stress, strain, and permanent deformation of the element or of elements? So these are two questions that we can answer by applying the load. So these two can be answered in separate. To shorten the video, we will cover these two parts in the next video. Yes, that was the end of this example. In this example, we calculated the yielding force of one rod, which is loaded somewhere between two supports, and we determined how we can increase the load until one element becomes yield, and then we have still capacity to increase the load until the other element is also yield. So in the next video, I will go through the reloading and the calculation of residual stress and the permanent deformation. Thank you for watching. See you next time.